Hello everyone, hope you are safe. This is Pega Garmani and I am presenting an alternative to MFCC for ASR. The other authors of this paper are Hossein Hadian, Daniel Povey, Hinek Hermansky, and Sanjeev Khodampour. The Mel scale is a perceptual scale of the frequencies. This scale is a handcrafted scale based on the physiological models of the human auditory system, and it's being used in MFCC and log filter bank, which are the most commonly used features for ASR. The joint feature extraction and acoustic modeling is the other approach that's being investigated in few studies. In this approach, it trains a model from the signal domain and the network crafts its own features in a data-driven scheme. The main drawback in this approach is that the network learns data-dependent filter banks and could overfit to the training data. In this paper, we propose a new set of analytic filter banks, which is estimated using the learned data-driven filter banks in the filter bank layer. These features are based on the filter banks directly learned on different narrowband and wideband datasets using the joint feature learning setup proposed in our previous work. The proposed modified MFCC features are the cosine shape filters, and each filter is specified using two main hyperparameters, which is the center frequency Fc and bandwidth W. And the proposed cosine shape filters have the bandwidth equal to W divided by 2 according to the noise equivalent formula. In MFCC, the center frequencies are calculated using the Mel scale, which is basically a frequency warping function. Here we propose a new warping function based on the filters learned in the filter bank layer. Figure 1 shows center frequency distribution for the filter banks learned on the switchboard AMI IHM, which are at 8 kHz and 16 kHz multi-English dataset. The multi-English dataset we used is a multiple English corpora consisting of Wall Street Journal, Switchboard, Hub4, Tedlium, and Fisher, where Switchboard and Fisher are 8 kHz and Wall Street, Tedlium, Hub4, and RD 16 kHz datasets. And we used the upsampling and downsampling of the data and trained the filters on top of these downsampled and upsampled data. As can be seen in the figure, the center frequency distribution probability is higher around the average of the first and second formant frequency. We propose a new set of warping function that's shown here that has two set of hyperparameter FB1 and FB2, which are adjustable and controls the first and second peaks in the center frequency distribution. This figure compares the center frequency versus the filter index for Mel versus modified Mel frequency. As can be seen, modified Mel contains more filters in low frequency subbands around the first and second formant, and especially around the hyperparameters we define on FB1 and FB2, which is set to 300 Hz and 1500 Hz in our modified Mel in this figure. We compute the bandwidths using two different approaches. The first approach is to approximate bandwidths using the fixed formula. In our previous work, the bandwidth doesn't depend on a number of filters. The main drawback in this approach is that some frequency regions, especially in high frequency subband, may not be covered by any filters. Also, enforcing a specific overlap between neighboring filters can cause the bandwidth to strongly be depending on the number of filters. This behavior is not mainly seen in low frequency subband for filters learned in the DNN. In our approach, we propose a new formula for bandwidth approximation, which is a combination of the two functions, a new function of the center frequency and a function of the filters overlap. BW linear in the first equation is not a function of a number of filters and is limited between two values PW mean and BW mean plus S of BW. And BW overlap is an overlap-based bandwidth which satisfies the minimum overlap between adjacent filters. In the next approach, we compute the bandwidth using the trainable DNN-based bandwidth approximation. In this approach, we use the DNN to learn the bandwidths. The filters in the filter banks layer are the cosine shell filters with a fixed set of center frequency defined in a previous slide. And as you can see, the filter bandwidth W prime are the only parameter that are learned using the DNN in this layer. The S-square function is used to impose positivity on the W prime. And we add a single layer with a per filter scale parameter after the filter bank layer to learn scaling values for each filter. In this part, we investigate the effect of different parameters on modified MFCC. In the first part, we investigate effect of f of B1 and f of B2 in center frequency approximation, where the BW mean and SBW that are used for bandwidth approximation are fixed to 30 and 60 Hz. Log and DCT transform are also applied on the modified Mel filter banks, where the dimension in all experiments is 80 dimension. As can be seen in this set of experiments, increasing the FB1 and FB2 to 900 and 3500 improved the result, especially on AMI SDM, which is a 16 kHz far field dataset, but it mainly degrades the performance a bit on the switchboard eval 2000 or RT03 test sets. Also, we compared the results using 40-dimensional feature in row 3 and row 4, and as can be seen, it can be shown that the result is less sensitive to increasing number of filter banks. In this part, we investigate the effect of BW mean and S of BW for bandwidth approximation. The table compares the results using different values of BW mean and S of BW, and the result shows that the word error rate is less sensitive to these parameters, especially on these two tests, which is tests for switchboard and AMI SDM. And also in all these experiments, f of B1 and f of B2 are set to 300 and 1500 Hz. We also use two different methods to combine linear bandwidths BW linear and overlap-based bandwidths BWOP. Two bandwidth values BWOP and BW linear are the lower bounds for the function proposed as G1, and also these are the upper and lower bounds for function G2. And BW mean and SBW are 30 Hz and 60 Hz in all these experiments. As shown in the first table, G1 produces better results, especially on AMI SDM. In the next table, we experiment different overlap values. And as can be seen, overlap value of 0.3 results in the best performance on 300 hours switchboard and AMI SDM. In this table, FB1 and FB2 are set at 300 and 2000 Hz for all experiments. Comparing row 1 with row 2 and row 4 shows that computing bandwidths using linear bandwidth formula with not considering the overlap results in 0.3 to 0.45% absolute word rate degradation, especially in the 16 kHz AMI SDM dataset. Also, comparing row 2 and 3 and row 4 and 5 shows that considering the linear part in bandwidth computation produces 0.1 to 0.3% absolute word rate improvement in our results. In this slide, we show the results for DNN-based bandwidth approximation. The center frequency for the filter banks in the filter bank layer in all these experiments are set using our proposed formula, and it is fixed during training. The bandwidths are also initialized using the bandwidth overlap value of 0.2 proposed in the previous slide, and the bandwidths are trained using DNN during training. Filter banks with a 50-dimension filter are used in the filter bank layer. And as can be seen, the computation cost in this approach is small, and the number of parameters added in the filter bank layer is equal to the number of filter banks. The first row in a table shows the order rate using our proposed frequency domain setup in our previous paper, where each filter in the filter bank layer in the old approach contains n divided by 2 number of parameters, where n is equal to FFT dimension. As can be seen, values of 500 and 3000 as FB1 and FB2 offers considerable improvement compared to the proposed frequency domain setup with the full filter banks. One reason is that learning the filter banks is sensitive to background noises and reverberation. Specifically, the parameters in high frequency region are not trained properly in the frequency domain setup. And the parametric filters are the regularized version of the full filter banks, and they are less sensitive to different noise conditions. And as can be seen, we can get nice improvement using this DNN-based bandwidth approximation approach, specifically on AMI STM. In this slide, we evaluate the performance of the proposed modified MFCC feature on various datasets. 80-dimensional modified MFCC feature is used in all these experiments, where FB1 and FB2 are set to 300 and 1500 Hz for warping function computation, and BW linear and BW overlap are set equal to 80 Hz and 30 Hz with the overlap value equal to 0.2 for bandwidth computation. As you can see, the comparison of the conventional MFCC and the modified MFCC shows nice improvement and gain, especially on the switchboard and AMI STM test sets while using this modified MFCC feature. In this paper, we propose a modified version of the MEL filter banks. In this approach, the warping function is a modified version of the MEL warping function with an extra hyperparameter to control center frequency distribution. The filter bank's bandwidths in our approach computed using a combination of a linear and overlap-based bandwidth formula. We also propose a method which consists of a parametric cosine filters with a trainable bandwidth, and we showed nice improvement over proposed fully trainable filters. Also, the results on different datasets shows 0.2 to 0.5% order rate improvement using new modified filter banks. And finally, I'm really thankful and appreciate your timing for listening to these slides.